We have a strange looking result here that it's a quotient that resolves for all prime numbers to a natural number, provided that p is not equal to 2. 2 is the only even prime, and notice that 2 doesn't make sense right here. You get minus 1 factorial, which doesn't make any sense in the discrete case. Now right here we mean positive integers. So we'll call that z plus if you want, all right? Z plus, and for all prime greater than or equal to 3 because of this case right here. Now here's some numerical evidence, and I won't go through all of it with you, but I tried it out for 3, 5, and 7, and we got natural numbers in all three cases, 1, 5, and 823. Okay, so it happened for the first three cases. That does not constitute a proof, but it makes us suspicious. There's a deductive proof right here. All right, now another way to re-express what we're trying to do right here is in this modular arithmetic format. Now this left-hand side here, if you want to call this top part the numerator, NUM, okay, NUM for the top piece right there, okay, the numerator. Another way of saying this that makes it look a little more believable, okay, so this top part's the numerator. So the numerator has to resolve to the product of two integers, namely p, and we'll call it m. So n would have, the numerator, I'll just call it capital N. Numerator would have to be in the form MP, okay, not military police, but some other natural number times the prime number, okay? All right, so again, n for numerator, you can rewrite this membership statement as just the numerator is equal to m times a prime. And you can just multiply formally by p, and then you're just a member of the natural numbers. We'll call it m, okay? Now that has the very same form as this, if you think about it, because this means subtract this entire part minus a minus 1 would be the numerator, and it would be a multiple of p, just like we've written right here. So this formulation turns out to be quite useful. If we can prove this formulation right here, we'll be done with it, okay? So let's move on down. Now here's the crux of it right here. There's two results right here that follow from Wilson's theorem, and you guys may have seen this, but you can re-express, if you think about what Wilson's theorem says and rewrite it like this, p minus 1, and then I'm going to go p minus 1 times the result right above is p minus 1 or p minus 2 factorial. Okay, that's p minus 2 factorial. Okay, now you guys, I'm sure a lot of you recognize this. This is congruent, exclam symbol right there. This is congruent to -1. Congruent to -1. Congruent to -1. Of course, we're talking mod p here. You know, let me make this a little more legible. That's a p there. Okay, that's as good as it gets. But you see, folks, this is Wilson's theorem because it would actually be, the left-hand side would be p minus 1 factorial. But notice also that since p is congruent to 0, trivially, right, p is congruent to 0 because p is a multiple of itself, namely 1 times itself, right? So p is congruent to 0. That would just leave this minus 1 right here. You would multiply through and you would get this statement right up here. Okay, now once you have this statement right here, this statement follows also because you would have a 2 left. That's where this 2 comes from, okay? So these two results end up proving this line directly above, right? Because remember, you can multiply congruences together. That is, let me just write this down. If you have, I'll just use the standard letters. If you have A congruent to B, all right, in other words, congruence behaves very much like equality. A congruent to B, and we're assuming a modulus of P here, but this is true for any modulus. And also B congruent to C, or excuse me, C congruent to D. Sorry, C congruent to D. I'm trying to use the trackpad because this mouse makes the screen move, so it's a little awkward here. But anyway, this is kind of a standard thing, you know, like in arithmetic. Equals or congruent to equals, so you would get AC congruent to BD, right? AC congruent to BD. Whoops. All right, so that should be D right there. And this is very familiar to the axioms of just the regular real numbers, you know. But you see, that's exactly what this does for us, because notice that if we take this and multiply it by this, we get this left-hand side. That would be the AC here, right? Which if we take the left-hand side, this, multiply by this, we get this left-hand side. And also, 1 times minus 1 is certainly minus 1, right? So these two statements, which follow from Wilson's theorem, along with this standard arithmetic truth from congruence, prove the result. Okay, so we can write QED right now. Okay, we have shown that this strange-looking result is true by establishing two corollaries of Wilson's theorem, then using this basic modular arithmetic statement or this axiom or this truth. It's a provable result. But anyway, and the proof of this, by the way, is non-trivial, but it's definitely true. So anyway, hope you guys enjoy.